possibility of Neptune, which is Poseidon in the old uh, Greek. I don't know about Uranus. I don't know what the Roman version of it is. Either way, each model is an approximation. Just like that, each model is useful in its own context. If all you wanted to know was uh, to predict the lunar eclipses and solar eclipses, you could have used the equations, the model of Ptolemy, okay, from essentially 2,300 years ago. I mean, even the ancient Sumerians, which was about 6,000 years ago, those guys had a pretty good idea about predicting the solar eclipses, lunar eclipses, and so on and so forth. But if you wanted to know uh, exactly where Neptune was going to be on the night sky 5 years from now, well, A, Ptolemy didn't have Neptune, and B, even if he did, that equation wasn't going to do anything for you. And you need Newton. But then Newton is not good enough to predict the orbits of bodies that are very close to Sun. So you need Einstein for that. In fact, any Star Trek fans around here? Have you heard about Mr. Spock? He's the Vulcan, right? So you know where the term Vulcan came? In the At the close of the 19th century, early 20th century, before Einstein published his general relativity, people were perplexed that Mercury's orbit wasn't conforming to Newton's predictions. He said, "Oh, just like we had in Uranus, presence of Neptune explained it. There must be another planet even closer to the sun than Mercury is. You know, it tugs on the Mercury's orbit, and they named that planet Vulcan. But nobody could ever find the Vulcan. And in 1915, Einstein publishes his equation, and his equation predicts exactly the orbit of Mercury that we observe. So depending upon what you want to do, models are useful. Now, the first thing we're going to do, we're going to start this simple case. In fact, I'm going to call this case 0. Come on. Let's call it case 0. Maybe I was using the wrong pen. Yeah. I mean, I don't take this model so not seriously. I'm just giving it a case 0. We're going to assume that dividends are constant. You are embarrassing me, computer. At the current level, and we're going to call that dollar D1. So I know that this company paid $2 per share dividend this year, and I expect that they're going to keep paying $2 from now until the infinity. If we simplify that infinite sum, the series sum, this becomes Sum I equals 1 to infinity, dollar $d1 divided by, or this is a constant gets out of the summation. Turns out that infinite series sum does converge. Okay. In fact, we know that this is exactly equal to 1 over r. You can actually do this for yourself. You know, it gets closer and closer to that number. So that means value of this firm is going to be next year's expected dividends over R. So if the company is paying a dividend of $2 per share, discount rate is 10%, then this company is worth $20. Okay. Obviously, that is not a realistic case. I mean, we know that all companies change their dividends over time, but it kind of gets us started. We're going to do our next case. Case one, constant dividend growth. Come on. So we're going to say we know current dividend, okay? And we know that next year's dividend is going to be current dividend times 1 plus G. So it's going to grow at the rate of G. And further, I'm definitely going to dump this computer to my son next year. He's going to be taking a gap year anyway. Now, let me type. I bought this computer so that I don't have to type. Dividends T plus 1 is equal to dividend T times 1 plus G for all G, for all T greater than 0. Okay. So every year dividends are going to go up by whatever that G percent is. So which means dividend T plus 1 can be written as, or dividend T can be written as dividend 0 now times 1 plus G raised to the power T. growth of t years at a rate of g, right? So if I use this, let me see if I can do it now. By the way, don't ever memorize that equation. Turns out this also converges, provided R is greater than G. Okay, and we can write this as this is basically a growing perpetuity, as we call it in analysis.